In this video, I'm going to explain some nonlinear functions, like power functions or exponential functions that you might have heard of, and also a little bit about logarithmic functions. Now, the thing is, these words, power function and exponential function, sound very similar, probably because a lot of people use the word power and exponent interchangeably, right? It's just the guy on the top, right? And so the difference is this between a power function and an exponential function is that a power function has the variable x in the base versus an exponential function has the variable x itself in the exponent. So that's the difference. So for example, let's look at this function. If t is your x variable, and you have 6t to the fourth as your, function. Well, that is a power function rather than an exponential function because the variable itself is in the base, not in the exponent. So that said, the way to deal with power functions, if I were to say, find the inverse of this power function or something where you wanted to manipulate this to solve for t, it's pretty straightforward as far as the usual algebraic rules will sort of get us there. Divide both sides by 6, so you could say r over 6 or 1/6 star, however you prefer to do that, equals t to the fourth. And then to get t by itself, you can just take the fourth root of both sides. So the fourth root of r over 6, right, same thing, is equal to t, right? So that's basically how you could deal with power functions. They're mostly the same algebraic processes. To get rid of an exponent, you just take that root of both sides. And new vocab word here, polynomial. A polynomial function is essentially multiple power functions added together. So for example, y equals 4x cubed plus 2x squared, right? That's two power functions added up, right? So you can have as many as you want, but the sum or difference of power functions is called a polynomial. A quadratic, which is a future video, is a type of polynomial where specifically the highest exponent on your variable is 2, right? So quadratic is the x squares. But yeah, so that's just, again, vocab and some of that. But let's now zoom in a little bit to exponential functions for a little bit. So again, as I said, the difference is that the variable itself is in the exponent. And what that does is that when we are trying to solve for it, our usual rules don't apply. So for example, if you had the function y equals, let's just keep it simple, 2 to the x, and I said solve for x, you basically have to take the x root of both sides. But then you still have x in like the root thing, right? X to the root of y equals 2. So usual ways for solving it won't really work. And so what we can do is we can use the inverse of an exponential function, which is called a logarithmic function. So the logarithmic function is just some new vocab words here while we're there. The natural log, the ln, of a number, and again, this video isn't the place for it, so I'm not going to go into the details there, but the short version of it is this. The ln of a number is just another number. So if I were to say, what's the natural log, the ln of 1,000, that's just going to be another number, and that number is a lot smaller. So the ln of 1,000, when you plug it into a calculator or something, it's going to be a number that's a lot less than 1,000. But the rules for the purposes of this is that the ln of e, where e is the number, in case you're not familiar, e the number, just like, pi is 3.14, e is essentially 2.72, right? Or 2.7182, it's infinitely long. But yeah, so e is a number, and so specifically in nature, a lot of things involve this specific number e, and so a common format of exponential functions, again, even though an exponential function can take any base it wants, right? Again, it's exponential as long as the variable is in the exponent. Even though, again, it is that generic, the most common type of exponential functions in the world you'll see is where the base specifically is that number e, 2.718. And so an example of an exponential function would be y equals e to the 2x or something, right? Or even the most simple one is just y equals e to the x, right? So y equals e to the x is an exponential function. And if I were to say, find the inverse here, meaning solve for x here instead of y, basically using this rule, the fact that if we were to take the ln of e to the anything, it's just equal to that something that's in the exponent. Here what we would do is we take the ln of both sides, the natural log of both sides. And especially in subjects like economics and policy, oftentimes people will just say log instead of natural log, but they mean log. In pure mathematics, there's a distinction between log, which is essentially around base 10, and natural log, which is around the base of e, which is what we're doing. But in econ, if somebody just says log, in a technical sense, they mean natural log, so often you'll just say take the log of both sides. But you mean take the natural log of both sides, because we deal with e. But anyway, so here, if we take the ln of both sides, the natural log of both sides, we get the ln of y, because again, it's an equation, so you gotta do the same thing to both sides, equals the ln of whatever's there, which is e to the x. And this rule says that the ln of e to the anything is just that whatever was on top. So here, this is just gonna equal x, right? The ln of e to the x is just x equals ln of y. And so this natural log function itself is again, it's the inverse because we can use that to solve for one over the other. And this rule also applies if you if you have the ln of something and if you take the e, so for example, a different question here, if I were to say, suppose you had ln of p equals p, and I said solve for p, how do you get p out of that ln, out of that log? Well, you essentially exponentiate both sides, meaning you basically put both sides as the exponent of e. You say e to the power of whatever this side was, ln of p, should equal e to the power of whatever this side was, t. Because again, if this guy really equals t, then e to the power of ln of p should equal e to the power of t. And our rule here says that the e to the ln of something is just that something, right? It's like these two cancels out and this becomes the main thing that it is. So here, e to the ln of p, the left-hand side is just p, and this is e to the t. So there you go. You basically got it out of the ln, right? So that's how that other rule works. But so now, a couple of final things. So let's just do one example of finding the inverse. So let's say you have this question that you have q, quantity, let's say, equals e to the 2p plus 5, and the question is find the inverse, meaning solve for p. So if the question here is just solve for p, what do? Well, you can take the ln of both sides and say the natural log of q equals, and then the natural log of whatever this is, e to the 2p plus 5. And remember, that rule says that the ln of e to the anything is whatever that exponent equals. So this, the right-hand side, again, here you could replace x with anything. So here replace x with 2p plus 5, and this rule still works. So the ln of e to the 2p plus 5 is equal to 2p plus 5. So here the right-hand side is just 2p plus 5. And the left-hand side is just ln of q. And now we can easily solve for p. Subtract 5 from both sides and divide by 2. So ln of q minus 5 is just going to equal 2p. And then, as I said, divide by 2. So you get ln of q minus 5 all over 2. Whatever that is p. So that is answering the question. We've solved for p. Okay? One final real-world comment on just exponential functions in general and why they're useful is in the real world, often, especially when we're talking about growth, it's usually exponential in many scenarios. It's sometimes linear, but usually when we're used to like linear word problems and stuff, like, oh, suppose the population of a country is growing by 80 people per year, right? And we're trying to plot a y equals mx plus b. And it's like, oh yeah, that growth, that's a number that's increasing, right? It's increasing by a constant amount for every x. That's the sort of defining feature of linearity. With exponential functions, exponential growth, if you were to graph out an exponential function like y equals, well, we'll get there in a sec. But essentially, the defining feature of exponential functions is a constant percentage change, a constant percentage increase, for example. So if I were to say that the number of people getting infected by a certain virus is growing, but it's not growing by the same amount of people every day that you're adding. It's growing by, let's say, 5% per day. Then essentially, your function would be something like, if you started off with like 80 people being infected and you're growing by 5% every day, that's going to be that times 1.05 to the x, where x is the number of days, right? So it's essentially you're increasing it by 5% every time period. Another form in which you could write this, again, this is not really crucial for what you need to know to answer a lot of these questions, but really just so that you're aware that there exists ways to really easily use exponential functions to model growth that's not necessarily linear, but rather changing by the same percentage for every period. So here, if the x-axis is just time each day, and the y-axis is the number of people infected, and you wanted to graph this out, it's going to start at 80, because, you know, when x is 0, you have 80, because e to the power of 0 is 1, and 1 times 80 is 80. You're starting off at 80, but then for every, when x is 1, 2, 3, 4, it's going to grow non-linearly, and that sort of exponential growth is sort of useful to model in a lot of real-world scenarios. And one final comment on all these, the relation between power and exponential functions is that in the long run, exponential growth always beats out power growth. So if I were to give you two different functions, let's say, and say y equals, you know, x squared versus y equals 2 to the x, you know, this one, if you were to graph both those out, and when x is a trillion, this exponential one is always going to be larger. In fact, even if these numbers are wildly different, even if I said y equals, let's say, x to the 1000th power, and y equals something really small like, you know, 1.001 to the x, when x is like 1, 2, 3, or whatever, this guy is way bigger, right? Like 2 to the power of 1000 is way bigger than this number, which is close to 1, right? But when x is like a trillion, when you go far out enough in your graph, this exponential function will always win out. So that means graphically, if you have a power growth function, like that's sort of looking like this, it's looking like this, the exponential function, even if it starts out low and low, it'll eventually have to cross, and at some point in the long run, exponential growth is always going to beat out power growth.